organize this with Patrick and my co-organizers in 2012. So it feels like I've been going around saying this is going to happen since negative infinity, but it's actually coming up very soon. We've even gone as far as starting to think about desk allocation, so it really is happening very soon. But if you're not aware of it, I mean, the Newton also welcomes visitors. If you're coming for a shorter stay and don't require a desk, it's possible to just show up. Talks, there's seminars every week, etc. And there's more information on our web pages. And I would assume people are interested in networks here. So I'm now going to be talking not about block models. So we heard a lot about block models from the previous speaker, and I've gone around talking about block models for a while, but we're going to be talking about other summaries. And this is joint work with Patrick Wolfe, who's also at UCL, and Pierre-Andre, who's sitting on the second row and looking embarrassed because I'm giving his slides. So whenever I say something that's wrong, it's probably not Pierre-Andre's idea. So we're going to be starting to look at large networks. So before, the excellent talk we heard just before me, we were very much focused on inference. We weren't thinking about limits as networks grew in sizes. We were thinking about, I mean, some of the results came up in terms of larger networks. We were thinking about inference or the network you were given, right? So we're now going to be talking a little bit about making sense of networks. And just to give you the basic terminology, even though we're all probably interested in networks, we're going to be looking at very simple structures. We're going to be looking at networks that either have linkage between a node or not. So there's a 1 if a node is linked to another node, 0 otherwise. And the way we like to think about these are as lots and lots of coupled coin tosses or Bernoulli trials where you're modeling certain success probabilities. And if you want to get interesting structures, you need to couple the tosses and come up with models that do that coupling in an interesting fashion. And one of the things we've been asking ourselves is, how should models become more complicated as the network size grows? And we talked already about the typical features of large networks. We're having large networks, obviously a large number of nodes. We're having a shrinking success probability. And Mark asked before, are these terminologies well known? Well, if you go back to the work by Bolobas and Reardon, they call sparse networks where the success probability is shrinking, but not order 1 over n, where n is the number of nodes, and extremely sparse networks, order 1 over n success probability. So that's going back to, I think that's Random Structures and Algorithms paper studies the extremely sparse network model. So yes, there is standard terminology. So having decided we're going to be studying large networks and we're going to think about sort of shrinking success probabilities and limiting objects, what do we actually need to put in place to understand such structures? Are there limit objects, and how do we summarize such limits? So that's the sort of questions we're going to be asking ourselves. And just as a little bit of background, we're going to be focusing in on patterns that we see in networks. So we're not going to be going to blocks as an archetypical pattern. So we're not going to be looking only at groups. We're here going to be studying what happens if we see particular features appear in the network, and as the networks grow in size, how do we expect these to appear? And nicely enough, Gesine has done a lot of work in this, very nice work in this topic. So just why is this difficult? Well, it comes back to the fact that networks are strongly non-Euclidean objects. So in a sense, you sort of go from structures that we all know, we're in standard Euclidean space, then we can go sort of mildly more complicated, we can be on surfaces of objects, and networks are even more complicated because you don't really have smooth surfaces or patches. This makes it harder to define simple summaries of network structure because you can't think of such easy patches, and it makes it even more difficult to compare structures of different sizes because if you put out the whole network, you can't really think of plonking it straight on top of another network and comparing it. So how are we going to be doing that? Well, we're going to think a little bit about what generates a network, and then we're going to be counting subgraphs or motifs in that network and asking ourselves, how structurally can we describe the network in such terms? So we're really going to be asking in what natural way does it make sense to study motifs, and how do these structures give us information? So this is, an idea that is not new. It goes back. There's papers by Allon and multiple other people, and we're going to be asking a little bit about what patterns we can detect. So just to give a little bit of a background to this, when we're talking about studying small structures in networks, again, the first question you might really ask is what patterns should you be using? Because if you're studying network structures, then you can define all sorts of little sub-patterns you might be interested in. And if we talked about social groupings, we see a typical feature up there, which is a triangle, which is if two nodes are connected, and or three nodes are connected and pairs of them are connected, you might expect all three to make up one unit. So we're going to be looking at counts of such patterns, and we're going to be thinking of characteristics of counting the frequency of a certain structure in a bigger graph. So it's very easy to imagine how to count, say, the number of triangles in a network. Counting a triangle is easy. As you get to more complicated structures, it becomes computationally a little bit more annoying to do the counting. But let's put that aside for the time being. So if we're going to be talking about limiting structures, let's first look back a little bit and ask ourselves what limiting structures make sense in terms of counts, and indeed this is not my work, it's sort of well-known work. So if you think about looking at the network as a sampling, so I'm keeping my notation there of A for the adjacency matrix of the network. If we're thinking of having a function and we're really taking samples of that function at all the values we have the adjacency matrix, which is a discrete structure, then you can ask yourself, as the network grows larger, in what scenarios would you think of a real network generated in a certain way to converge into a function? And people have studied about the appropriate metric or distance to ask such questions. And you come to the cut norm, cut metric, and that can be related to the subgraph distance, where instead you look at renormalized counts and start to ask how they're different between different graphs. So instead of looking at whole networks, which might be generated from some limiting object, you ask yourself, oh, if I renormalize the counts, so I've gotten, do I actually have a little pointer? Pointer? Yes, no? I'm known for standing and jumping around. It's dangerous here. Maybe you won't be able to hear me. So when I'm counting, so this is just when I'm defining a renormalized count, I'm just comparing how many times do I find, say, the triangle in network G compared to how many times would I find the triangle in the complete graph, which has every linkage. And this indeed tells you how frequent is the triangle, say, compared to the most you might get. And you could compare the counts because they're renormalized between networks of different sizes, and that would be fine. We talked a little bit about sparse networks. Mark talked about when it becomes difficult to infer block models. So defining renormalized counts to compare proportions of counts for dense networks is what leads us to the previous page. In reality, you think that the number of edges actually doesn't scale as fast as quadratic, and instead you have a shrinking success probability of having an edge. And instead, you can now redefine a new proportional measure, which has the side effect of no longer lying between 0 and 1 as a proportion. And comparing such measures between different networks can again help you to characterize what is a typical network. And again, I was mentioning these papers by Bolabas and Reardon, and they describe when you can define such renormalized quantities and when they have nice limiting behavior and all of that. And the reason I'm telling you about this is because we're going to continue to study counts, namely counts of subnetworks in a bigger network. But I just wanted to reassure you that if we think about such things between networks as different sizes and networks as different sparsities as the objects grow in size, in fact, all of this makes sense. As a little aside, you can define these proportions in two different ways, that's sort of two standard ways of defining proportions, and one of them makes sense for sparse networks and one of them doesn't. But that's more of a curiosity than anything else. And the two different proportions you get behave the same when you have a dense network, so it doesn't matter which you choose. Okay, so we talked a bit about counts, and counts are nice. But does it perhaps matter where you find the counts in the network? Because one of the big problems a little bit with defining these summaries is we've decided we want to compare structure in a network between different networks, but it's really irrelevant if we look at the global count, or are we interested in local counts? So you could think about any type of motif of treating any node separately and then look at counts of a particular structure given you've rooted it. You can have a routing of the motifs in a given location. So you can really here think about the structure associated with a sort of center node, if you'd like, or not. What happens then? Well, you can go back to still having a graph of interest G, and you can fix it, and you can look at counts of a certain structure when you fixed one of the nodes in the structure. So we can decide to fix a given node I, and then just ask ourselves, if we count that motif in the graph, but we fix one node, how does this structure change? So what's that giving us? Well, it's giving us the ability to differentiate what's happening in different parts of the network. And this is related to sort of partial labeling of graphs, which again you can look at more at in Lovatch. Having done so, you can again ask yourselves, how would I renormalize things? So before, we saw that we needed to renormalize by a certain fraction of rho, which was the probability of having an edge anywhere in the network. And this ratio edges is giving you the same thing. If you have the edge just in the number of edges in G compared to what you'd have in the complete graph with the same node size, you're exactly getting back the power of rho. But you can again count how many rooted graphs of a given type do you get compared to what you would get the complete graph. So having done so, you can go back and start to ask yourselves, how would that relate to having a limit object? So we talked about limiting objects. Basically, if you have a real network, so let's just pretend this is a real network. It's not a real network, it's a generated network. So pretend this is a real adjacency matrix where you have two axes, I and J, and you're looking at linkages between nodes labeled I or J. Well, one way of generating such networks is to use a kernel function. Just evaluate the function at the random location, say here, and then generate the Bernoulli trial with that success probability. So that gives you a whole way of being able to think of a limit. And in some of my previous work, I found methods of estimating that function by using exactly block models. And in a sense, that connects up the previous talk we heard with exactly what's going on here, where we're trying to characterize the network. So having gone round. So we're going to call the kernel kappa. And what we can do, once we've decided we're going to define a renormalized version of the rooted count, we can exactly relate this object in expectation, once we sort of account for the Bernoulli rule noise, to what we would get from kappa, the kernel of the network. And what we find when we calculate this ratio exactly from the sort of sample of the real network and compare it to an idealized quantity defined from using the kernel exactly, is unsurprisingly you find that the counts converge in distribution to a Gaussian random variable. So that's exactly related to some of the work Gesina's looked at, where she's looking at unrooted counts and looking at convergence, unless I'm misrepresenting her. So under the same assumption, you can basically start to look at functions of the counts, and again using standard theorems which I won't go into details of, we can find that we can do functionals of the counts that have been renormalized, and again find that whole collections of them converge to a Gaussian distribution. So you might say, great, that solves my rainy afternoon problem where I want to derive new distribution because I've got nothing else to do because I'm stuck in Stockholm, say, my hometown, and I want to derive limit theorems for an afternoon. But what can that actually tell us about real networks? Well, let's skip that one. Let's imagine for a little while that we're looking at real networks. So what you see on the top row are realized real networks, either coming from a simple model which just has a structure which depends on a marginal probability of connection or a proclivity for connection. We got a stochastic block model which has marginal proclivities added on. And we have on the right-hand side the final group of models that Mark talked about, which is a mixed membership where each person connects to another depending on sort of what set the model that relationship had made you attached to, right? So these are all different network models that you can ask yourselves, okay, we've looked at calculating summaries from a network by looking at triangles. We can also look at simpler summaries such as just average number of degrees. And we can ask ourselves, in aggregate, if we look at all of these different models, do we find, how do we see the difference between the actual realized triangles and degrees? And we can do this rooting so we can detect different local phenomena that are present in all the networks. So we can start to characterize the properties of these models. And as I said, this is not a completely unrelated idea to what people have done before. We looked at proportional counts just before, and people have created, in a sense, exponential graph models in order to exactly capture certain moment behavior. So these are not starting from such models, they're starting from the standard framework of kernel-based models, and they're saying what properties do actually counts have and what additional features are we going to get out by starting to root. Okay, so we looked at the convergence of the distribution to the Gaussian. We looked at the relationship to the latent model that we saw. I'm not going to forget my pieces of clothing because I randomly go and leave my jackets in various places. What can we actually practically do with this? So we had a nice kernel-based model. Unfortunately, in real life, most networks are not generated from nice kernel-based models. We had a nice Gaussian distribution that came as the limit. All of these are just null characteristics of the model. So one possibility that we can look at is to go back to these vector characterizations where we looked at taking basically average of functions and getting a vector characterization of the proclivity to have triangles or degrees or any more complicated shape, and we can derive what null distribution we expect, which will get us a multivariate normal. So if we have nice data, then if we look at generating a single, just looking at degrees and triangles, we can create a score by taking account of both the covariance between the degrees and triangle and doing the old trick of creating like a single quadratic, taking account of the covariance of the triangles with the degrees. And if we generate from the right model, we're going to get something very well behaved, where if we put in the red ring, accounting for the fact that we have multiple realizations, all of the realizations we see are nicely going to lie within that typical mode of behavior. Now imagine we're actually altering, generating things nicely from a kernel-based random model, and we're going to alter exactly one of the observations so it no longer falls into the generating mechanism exactly. Then we're going to be able to detect the outlier exactly because it no longer conforms to standard behavior of typical structure between renormalized degrees and renormalized triangles. So it's a way to detect unusual or abnormal behavior which doesn't conform to the whole network being homogeneous. If we take a look at real networks, well, the real networks seem to behave like these simple models predict that they're going to behave like. Well, if we take a look, what we find is quite a lot of additional structure that's present in the network. So we can then see a whole proclivity for both having more triangles. We have degrees and triangles, and we can capture if there's a lot more structure in terms of 4 triangles than you would expect from a simple null model. And you can see in both of these cases that things don't behave symmetrically in degrees and triangles. And indeed, there are more triangles than you would expect. You have to take some additional things into account when you start to look at network features like this. So for instance, some relationships between degrees and triangles are known to be constrained, like the Turan theorem, and you can't have, if you change the number of degrees overall, you can't arbitrarily put in too many or too few triangles, because there is a lower and an upper limit in the relationship between the two quantities. But even so, you can derive what appears to be an unusual amount of one given the other. So generate from the model, everything behaves like you expect. Knock only one relationship out of line, you can detect it very easily. And of course, as with most things, network assumptions and network models aren't really captured all of the features we see in real data. I mean, unfortunately, these are 2 examples which are Podblogs is actually generally a very nice network which will give you almost exchangeable-like characteristics for most properties, but you see in terms of triangles here, we're not really doing very well at all. Taking a few more collaborative networks, which we've seen previously, as well as the net science data set, continues to reproduce these structures. And unsurprisingly, as I'd say, the relationship with degrees and triangles, you wouldn't expect to see strong symmetries, just because extremal graph theory will tell you that you can't have completely arbitrary relationships between degrees and triangles. And that's another reason where for ergoms, for instance, you get failure when the network gets too big, because a lot of the time you're trying to push them out of the relationships between degrees and triangles that you're allowed to have. And then the network has to go pathological, because you're trying to fit something, you're trying to force something to happen, you're trying to put the model to enforce conditions between degrees and triangles which were never really meant to be there. And of course you get something extreme, and there's a nice paper by Chatterjee and Diaconis which explains this in very mathematical terms, which must now be about 2 or 3 years old. So, I have been speaking way too fast, but it's definitely put us back on time, so we won't be late for coffee. I think the basic philosophization which you get before you have a few minutes to ask me questions is, we're all coming up with different ways of creating summaries or describe network structure, right? Block model is one possible approach to this, where you're trying to look at an aggregate group structure. Motifs are the very extreme opposite end. You're trying to describe something very small scale, very small feature on aggregate in your data, and unfortunately, it's very easy to try to force relationships or assume relationships that are very extreme, and so you're trying to capture or deal with very low-level feature of your data. I think one of the big outstanding problems is to go in between the two, right? The block model, in a sense, is putting on something order n on the data. It's forcing most block models that people fit try to use blocks that have a size which is on the same order as the whole data set. Motifs, which describe additional important structure in the data, are really order 1 feature. So what I think you need to reproduce a lot of patterns you see in real life is, how can you get a model that reproduces features in between what's order n, and what's order 1. But we certainly will always, when we're trying to understand data, we'll look at order 1 features, because it's what we expect to see in people. So if we are interested, say, in social relationships between people, things like triangles and degrees will greatly capture our imagination. If we're looking at the farther distance, we'll end up with order n type of relationships where we're trying to describe extremely aggregate features. And the problem is to mush it all together to get a realistic degree of structure in data. Thank you.